Hello, welcome to ANA community. From the past several videos, we are discussing about the concept of electrocardiogram. Initially, we have discussed what are the indications and contraindications of electrocardiogram. And later, we have started with the normal ECG as such that actually included about the what are the different waves and what are the different normal intervals and what do you mean by segments and what do you mean by the J point, etc. What are the normal values we have discussed. In the next video, we have discussed about conventional leads, the 12 conventional leads. What do you mean by the frontal plane leads? What do you mean by horizontal plane leads? What actually recording the ECG from those different viewpoints, what will be the indication, what we will going to understand, we have discussed. In today's video, we are going to discuss some of the fundamentals of electrocardiogram. As we have started from the beginning, we have discussed some of the simple aspects of ECG first, and now we are going to discuss about some of the deeper concepts of electrocardiogram. When you think about the fundamentals of electrocardiogram or ECG, we will be going with a little bit history and some of the physiological aspects, why these particular wave patterns occur, and what do you mean by the depolarization, etc. We are going to see, and what do you mean by the vector, and in what ways this is helpful in doing or in analyzing ECG, etc. We are going to discuss in this particular video. The person who has invented ECG is William Einthoven. Based on his understanding, so there is one particular term called Einthoven's triangle is being derived. William Einthoven is the person who has used string galvanometer to assess the electrical current from the heart, the two in the 1902. Electrocardiogram, which is also being termed as ECG, in some of the occasions that is being termed as EKG. It is the graphical recording of the electrical potential produced by the cardiac tissue. The who will be recording these electrical potentials? The electrodes placed on the different parts of the body, that is placed on the limbs and the chest. These electrodes are being placed and they are recording the electrical potentials. Electrocardiograph is the instrument that is used to record electrocardiogram. This is the person who is considered to be invented the electrocardiogram, William Einthoven. This is the first ECG machine. See the mammoth size of electrocardiograph in that particular olden days. Nowadays, that is becoming shorter and shorter, smaller and smaller ECG machine. When you think about the presentation of human body, suppose if you are saying the heart is being situated at the center, so that will be actually responsible for the contraction of the myocardial muscle. So that will be responsible for the movement of the electrical potentials into all the directions. So that is being depicted by the yellow colored image in the center of the human body. The same thing that can be equated to a box. So wherein in the center of the box, heart is being located. From there, multiple directions, the depolarization. What do you say that the waves will be moving from the center to the periphery? When you think about the anatomy of the heart, so that is having the two chambers, that is basically biatria and biventricle. Though they are having four chambers, right atria, right ventricle, left atria, left ventricle, but both the atria are functioning as one chamber itself, and both the ventricles are functioning as one chamber itself. And when you think about the movement of the blood, deoxygenated blood will be moving in the right side of the heart, whereas oxygenated blood that will be moving in the left side of the heart. So superior vena cava and inferior vena cava will bring the deoxygenated blood from different parts of the body into the right atrium. From there it will be entering into the right ventricle. From there it will be entering into the pulmonary trunk. From the pulmonary trunk it will be moving into pulmonary capillaries. From the pulmonary capillaries there will be the exchange of the carbon dioxide and takes place so in place of oxygen to become oxygenated blood. This particular oxygenated blood that will be moving from pulmonary capillaries into the pulmonary veins. From there it will be entering into the left atrium. From there it will be entering into the left ventricle. From there it will be moving into the aorta. From there it will be moving into different parts of the body. This is what we can say the brief functional anatomy of the heart. When you think about the electrical field of the heart, that is being mentioned that the heart is situated at the center of the electrical field, as we have said in the image, wherein at the center the heart is being located. From there it will be responsible for the movement of these electrical potentials to different parts of the body. When you think about the electrical field, the electrical potentials generated by the cells which are nearer to the electrode, that will be responsible for the increased amplitude of the deflection in the electrocardiogram. Whereas the distance is being increasing from the heart, that will be responsible for the gradual reduction in the deflection happening in the myocardium. When the distance is more than 15 centimeters from the heart, the decrement or the decrease in the intensity of deflections will be very, very negligible, or it is very hardly noticed. That means there is no potential difference that will be made by the electrodes if they are placed more than 15 centimeters from the center of the heart. This one we have to remember, where we are going to think of how this Einthoven's triangle is being developed. This particular principle will be helpful in determining the application of Einthoven's triangle. When you think about the position of the heart, this is the same. The heart is situated in the center, and that will be responsible for the electrical impulses will be generated in the heart. From there it will be moving into all the directions. From the center of the heart it will be moving in different directions, and this one we have discussed in the previous slide. There will be no any change will be noticed if the distance is more than 15 centimeters. That means if the electrode is placed 20 centimeters from the center of the heart, no much difference. 30 centimeters from the heart, no much difference. If it is present at the 10 centimeter, then that will be responsible for the increase in the amplitude. 14 centimeters, comparatively little bit decrease in the amplitude than 15. That means there will be a slight increase in the amplitude. If it is placed at around 10 centimeters from the earth, there will be even much more increase in the amplitude of the electrical potential. When you think about the electrical field, initially that will be generated by the sinoatrial node. This is what we can say the sinoatrial node. From there impulse will be generated. From that it will be moving into atrioventricular node. This is what we can say atrioventricular node. It will be connected by bundle of his. From there it will be moving into right bundle branch and left bundle branch. From there it will be moving into Purkinje system. This is what we can say the electrical potential will be conducted in the myocardium. When you think about the electrocardiographical importance of the anatomy, as we have discussed in the earlier slides, the heart has, though 4 chambers, it will be acting as two chambers only, that is biatrial and biventricular. This particular difference in the anatomical positioning is done by the fibrous atrioventricular ring. This is actually differentiating the biatrial chamber and biventricular chamber. That means both the atria will be functioning as together, whereas both the ventricles, they will function as together. When you think about the ventricle, among the 4 chambers of the heart, specifically ventricle is considered to be the dominant chamber. And when you think about the right ventricle and left ventricle is almost 3 times larger or thicker than the right ventricle. That means the thick ventricle is 3 times the thinner walled ventricle. And left ventricle, as it is a dominant structure, here the hemodynamic action, that is the movement of the blood from the left ventricle to aorta, that will be happening via left ventricular pumping. So here the smaller image, which is being mentioned in Gray's anatomy, this is being depicted there. The right ventricle, the wall is very thinner, whereas left ventricle, the wall is much more thicker, almost 3 times than that of right ventricle. So here you are going to see the chambers, biventricular chamber. So here interventricular septum, it is actually continuing with the free wall of left ventricle, whereas the free wall of right ventricle will be attached to left ventricle. When you think about the thickness of the right ventricle and left ventricle is almost 1/3 of the left ventricle. Hence, that will be playing a very minor role in the pumping action of the heart. The one which is playing a major role, that is left ventricle. When you think about the electrical activities, their conduction, that will be generated in the sinoatrial node, or what we can say SA node. From there, it will be moving, the electrical potentials, they will be moving into the atrioventricular node. From the atrioventricular node, it will be moving into the bundle of His. From there, it will be moving into the right bundle branch and left bundle branch. From there, it will be moving into the Purkinje system. These are what we can say the electrical potential and their action in the human body. When you think about the production of ECG waves, there are 2 types of the processes that will be happening in the myocardium: atrial events and ventricular events. Atrial events, they will be acting as synthesia. Synthesia in the sense, all of them, they will be acting simultaneously at a particular time. Whereas ventricle, they also act as synthesia. Atrial events, they are going to take place from the electrical potentials, they are generated from the sinoatrial node, that will be moving into atrioventricular node. Whereas ventricular events, they are going to get generated from the atrioventricular node till the Purkinje system. When you think about the activation of the atria, that is actually done by sinoatrial node. That is a natural pacemaker situated in the upper part of right atrium, which is actually generating the electrical impulses spontaneously. From there, that is from sinoatrial node. The electrical impulses they travel from sinoatrial node to AV node through three conduction pathways: anterior, middle, and posterior internodal pathways. From there, the impulses they are moving to the atrial cells. Whereas activation of the ventricles are concerned, from the sinoatrial node we have discussed there will be the transmission of impulses that will be up to atrioventricular node. This will be followed by a slight delay among the transition from the atrioventricular node. The activation of the myocardium that happens in the bundle of His. From there, it will be moving into right bundle branch and left bundle branch. Left bundle branch, they are again divided into two: anterior fascicles and posterior fascicles. Because of which impulses they will be moving into anterior and posterior portions of left ventricle via Purkinje system. This is about the atrial as well as ventricular activation, wherein atrial activation that will be happening in the longitudinal direction, whereas ventricular activation that will be happening in the what do you say, that width-wise depolarization that will be happening from the endocardium to epicardium. The movement of this electrical potential will be happening in the ventricles. When you think about the organization of human body, this is very, very essential to know about the composition of the human body. It actually contains three main constituents: water, solid portion, and electrolytes. Water portion that will be present up to 60% of the human body, whereas solid components they are present for 38%. Electrolytes present in the human body will be up to 2%. Whereas intracellular fluid that will be present up to 66%, and extracellular fluid that will be comprising of 33% of the human body, which includes intercellular fluid, intravascular fluid, fluid of the mesenchymal tissues, and transcellular fluid. When you think about the fluid composition, intercellular fluids as well as intracellular fluids, they are electrolytic solutions. They contain the cations like sodium, potassium, and calcium. They contain the anions like chloride and bicarbonate ions also. As far as electrical physiology of the myocardium are having four events. The first event is impulse formation in the primary pacemaker. That means impulse formation in the SA node. Or if the SA node is not functioning, AB node that will be taking the role of the pacemaking function. From there, the transmission of impulse that takes place through the specialized conduction system, that is what we can say the bundle of His and right and left bundle branch. Next, there will be depolarization of myocardium. It is followed by repolarization of myocardium. When you think about resting membrane potential, this is the potential difference that will be present when the myocardium is at rest. This is actually having the polarization of the ions, wherein the more amount of the sodium ions they are present outside the cell, and more amount of the potassium ions they present inside the cell. When you think about the polarity in the fluids, because of the excess presence of potassium ions inside the blood, they are usually considered to be having negative potential. Whereas outside the cell, they are considered to be positive cells, which are actually generated by the what do you say that sodium ions in the interstitial spaces. This particular resting membrane potential in most of the cardiac cells they occur, except in the sinoatrial node and atrioventricular node. Normally, the resting membrane potential in most of the cardiac cells will be up to minus 90 millivolt. From there, that will be responsible for the change in the polarity. Before change in the polarity, we need to know about the sodium and potassium concentrations in the interstitial spaces as well as intracellular spaces. So here the intracellular potassium ion, they are present up to 150 milliequivalents per liter, whereas extracellular potassium ion, they contain 5 milliequivalent per liter. That means 30:1. Whereas extracellular sodium ion concentration, it will be up to 150 milliequivalents per liter, whereas intracellular sodium ion concentration will be up to 15 milliequivalent per liter. This is actually maintained by sodium potassium pump. So here there is an image of a myocardium. Suppose if there is any movement is under resting membrane potential, the more amount of the negatively charged ions they are present inside the cell, and positively charged ions they will be present outside the cell. That means inside the myocardium and outside the myocardium. This will be actually maintained by sodium potassium pump. When you think about the graphical representation of the ventricular depolarization or ventricular activity, that is this is considered to be the graphical representation. On the y-axis, that is considered to be the what do you say that the potential differences, and on the x-axis that denotes the time parameter, wherein the 0 considered to be depolarization as such. 1, 2 and 3, they are consisting of what do you say that repolarization events, and 4 is considered to be attaining resting membrane potential. So these are the activities that is happening in the myocardial cell. That too, this is happening in the ventricular cell. Whereas in the graphical representation in case of the atrial cell, again 0 considered to be a depolarization wave, 1, 2 and 3 that is considered to be repolarization wave, and 4th that is considered to be attaining resting membrane potential. This is the representation of the depolarization and repolarization in SA node and AV node. 0 is considered to be the depolarization effect, and 4 is considered to be the repolarization effect. And resting membrane potential will be following the depolarization wave. This is considered to be the graphical representation in Purkinje system. Again, 0 depolarization, 1, 2 and 3 that is considered to be repolarization, and 4 is considered to be restoring the resting membrane potential. Now, what do you consider it as? What do you mean by depolarization? The term polarity refers to the concentration of certain groups are present in one particular place. Depolarization, the term refers to the change in the, what do you say that the polarity. So as we have discussed earlier, when you think about the myocardium, in the interstitial spaces, there will be more amount of the sodium ions. Whereas inside the cell, there will be considered to be the more amount of potassium ions, which is actually responsible for the change in the potential differences. from minus 90 to plus 20 millivolt. This is actually designated as phase 0. And this is actually reflecting the fast inward current, which is actually specifically seen in myocardial cell and Purkinje system. Whereas depolarization in the pacemaker cells, that will be known by 0 and 4, wherein 4 actually representing the repolarization and 1 is actually representing the depolarization wave. When you think about the repolarization, again it is having 4 phases. The fourth is actually re-establishment. That means it is having only 3 phases. The first phase actually that is considered to be initial rapid return of intracellular potential to 0 millivolt, which is actually happening because of the closure of sodium ion channels. In phase 2, there will be a plateau phase because of slow entry of calcium ions into the cell. And phase 3, wherein intracellular potential to resting memory potential, there will be an initiation. That means there will be efflux, that means outward movement of potassium ions from the cell will happen. Phase 4, actually, this is considered to be restoration of a resting membrane potential. These are the 4 phases that you can see, phases of the depolarization, repolarization of a myocardium. When you think about threshold potential, it is a kind of the potential which is considered to be responsible for the myocardial depolarization when there is activation or excitation of cardiac cell occurs because of a stimulus, wherein the threshold potential in atrial and ventricular cells will be minus 60 millivolt, and in cases of sinoatrial and atrioventricular node, that will be having minus 40 millivolt. If the resting membrane potential is increasing toward the level of threshold potential, there will be a weak stimulus which can evoke a response of a depolarization. Suppose if the depolarization is occurring here, then you are not going to have adequate, what you say, that the depolarization as such. Whereas if resting membrane potential is lowered away from threshold potential, there will be a stronger stimulus that can evoke the depolarization as such. Suppose if the depolarization is starting somewhere here, that will be responsible for the increase in the stimulus of a myocardium, and there will be the evocation of response will happen. As far as refractory period is concerned, 2 types of refractory period are there. Absolute refractory period, where no stimulus of any activity can evoke the depolarization wave. Whereas relative refractory period, which is considered to be a stronger stimulus that can evoke the depolarization response. Now we are going to see what do you mean by this, the refractory period, absolute refractory period and relative refractory period. So when you think about absolute refractory period, so here that is considered to be 0, 1, 2, part of 3 are actually considered to be the area where depolarization may not occur if you are going to make a stimulus of myocardial cell. During this particular time, the sodium channels which were activated during depolarization become inactivated, wherein the relative refractory period is the one where the membrane potential reaches the threshold potential and ends just before the termination of phase 3. During this time, if you are making a stimulus, that is responsible for the depolarization wave. Now we are going to see about the vector. What do you mean by vector? Suppose if this is a football field, there is a football in the center, but what about the goal as such, that is the goal post of a opponent's area. So that means the ball can have the movement at multiple directions, but its sole aim is to attain the goal post of the opponent team. In the same way, the cardiac depolarization is also considered to be a vector because it is moving in a certain direction. When you think about the myocardial cell, there are two myocardial cells, and there is a stimulus that is going to take place in the middle of those myocardial cells. And if you are keeping a positive electrode on the either sides of the myocardial cell, the area where that is being produced in the, what do you say, that the moving towards that particular positive electrode, that will be responsible for the prominent positive deflection in the electrocardiogram. But here there are two such images which are having two equal sized myocardial cell, and you are keeping the electrode on both the sides of the myocardial cell. These are responsible for the prominent positive deflection in the ECG complex, ECG read, ECG paper, because the stimulus is happening in the middle. Suppose if there is a, what do you say, that the two dissimilar myocardial cells, and you are keeping the electrode on the either sides of these myocardial cells. The one which are having the smaller, the myocardial cell, first there will be the prominent positive deflection, which is followed by the deep negative deflection. That means that is responsible for the prominent, what do you say, that the small r and prominent S wave in the ECG recording. Whereas the other area, that's a larger myocardial cell, that is responsible for the prominent positive deflection. There is no negative deflection will be there because of the myocardial cell size. When you think about the electrical potential, that is stimulus is happening in the somewhere at the end, and you are keeping an electrode somewhere in the middle of the myocardial cell like this, that is responsible for the prominent positive as well as negative deflection. Because whenever if you see that there is a stimulus is moving, that is actually nearing the particular electrode. When that is moving away from that, that is actually responsible for the movement happen away from the, what do you say, that particular electrode. That means initially there will be a prominent positive deflection. This will be followed by prominent negative deflection. When you think about the repolarization, if the repolarization is happening in the same direction of the depolarization, that will be responsible for the prominent negative deflection. If the repolarization is happening in the reverse direction of the depolarization, that will be responsible for the, what do you say, that the prominent positive deflection, right? Or if the electrical impulse is moving away during depolarization, and in the same direction if the repolarization is moving, that will be responsible for the, what do you say, that the downward deflection. When you think about the direction of electrical potential in the atrial depolarization, that is this way. That means downwards, inferior and laterally. This is what happens during septal depolarization from left to right. This is how the depolarization occurs in the ventricle. That means left side inferiorly on the left side. That is actually happening in the ventricular depolarization. Whereas ventricular repolarization normally happens in the reverse direction. Hence, the QRS complex as well as T waves will be in the same direction. This is what we can say Einthoven's triangle. So here the particular Einthoven's triangle is derived based on the concept of the depolarization. That is what we can say the electrocardiographic recording is happening, where the lead are being placed 15 centimeter away from the heart. So that means, as per this particular principle, if any lead is being placed 15 centimeter away from the heart, there will be no difference will be in the electrocardiographic deflections will be taking place. That means when you are keeping the right arm, and left leg electrodes, as they are present more than 15 centimeters from the heart, there will not be any electrical potential difference. Based on that, we can able to make what you say that equilateral triangle. This particular equilateral triangle is named on the person who has invented electrocardiogram, that is Einthoven triangle. And the electrical potential of a closed circuit will be 0. This one we need to remember. From this particular Einthoven triangle, in the next two videos, we are going to discuss how to draw a hexaxial reference system. So, the take-home messages from today's discussion are ECG, or otherwise termed as EKG. It is a graphical representation of electrical potentials generated in the myocardial cells by the electrodes which are placed on the surface of the heart or surface of the body part, specifically limbs. Depolarization, repolarization in the myocardial cells is the mechanism behind the ECG deflections. Depolarization and repolarization are considered as vectors, as they are having both magnitude as well as direction. Depolarization is not equal to atrial or ventricular systole, and repolarization is not equal to atrial or ventricular diastole. Atrial depolarization will be followed by atrial systole, and ventricular depolarization will be followed by ventricular systole, and ventricular repolarization is followed by ventricular diastole. Dear ANA community, that's all for today. What are the major key takeaways from today's discussion? Mention in the comment box below. And what is the one video that you would like to hear in the coming days? Mention in the comment box below, and spread this particular video to maximum number of true Ayurveda learners or true Nidana learners, so that we can make a huge movement out of this particular small message. That's all for today. Something more in the next video.